Hello. Okay, so today I'm going to show a little bit of lean. The idea is that yeah, you cannot see anything, right? Okay. So first thing. Okay, so we're in the classroom, but we cannot turn this light off apparently. But the major problem was the size. Maybe, but is it still readable? Is it forever? Yeah. Okay. I'll show you what you're supposed to do next, or what you were supposed to be doing along some of these lectures. So let's start playing with lean, and let's start by pretending that we are downloading lean. Most of you, I hope, have already done this. So you go to the lean website, and I suppose you click on install. I have already installed lean, and I have already installed the next thing I'm going to show you, because I didn't want to spend time doing this here. But okay, so let's say you installed lean, and you see here in the instructions somewhere, okay, I suppose it's here. It's like 3 steps. First, you install VS Code. You may already have VS Code. If you don't, install it. Then you install the extension of lean inside VS Code, and pretty much the extension will take care of doing the rest. And if you want to use some other editor, you're allowed to, but the community of lean has strongly focused on VS Code, and it has surpassed the features that you may find in Emacs or Vim. That's it pretty much. Okay, so suppose you have installed lean. There's some kind of documentation stuff that you can read, and there's a very quick tutorial thing that I want to go through with you and discuss some things. It's called Glimpse of Lean, and there you go. Can you see anything? Okay, it's weird. For me, it's weird that you can see it. I can hardly see something here on my screen, but anyway. So yeah, I will not go through how Git works, and I just want to make it clear that you don't need to be an expert in Git or even know what it is pretty much to start using it. It's a very complex system, but luckily you only need to know like 2 or 3 things to get started, and then eventually you will feel the need that something should exist in this program that you have learned a tiny bit of it. And then you will realize that it already exists, and you will find out how to do it. But I mean, don't think that you have to study first a book on how Git works and how you can be a master of Git, and then start using it. Okay, it's like you learn 2 commands, and you will keep using them for a year or so, and then you will feel the need to ask for the 3rd command you will use. Pretty much. It depends on what you do. I mean, if you're a developer, you obviously already know Git, but if you're a mathematician, maybe you haven't even heard of this. And so pretty much what Git does is it keeps track of a project that you're working on, be it your diary or a program or your thesis or whatever, in the sense that at any point you can ask it to go back in time, and you can ask what changed from this version to that version, and when was this line introduced, because you're looking at this line and you think, what was I thinking when I wrote this? And it helps a lot with collaborations as well, but in this I mean, for the time being, I suppose that you're working by yourself, and still it's extremely useful to have this. And I will not go through this, but the idea is that we will at least use it to download this project. So okay, a bit more of Git things. Along with Git, there are some places, a very famous one is GitHub, where you can put your projects there, and other people can download them, suggest fixes, or contribute, things like that. So the first Googling that I did was okay, I even had a typo here, it's Glimpse of Lean, and then I go to the first thing, which was exactly the repository, as we say, that I wanted. And the idea is that, okay, one of the ways to do that is like you copy it, and then you go back to your terminal. Please don't be scared of this thing. And then you find some directory that you will work for lean, let's say it's called lean, and you do something like git clone this thing. And once you execute it, it will start fetching all those things from there, and eventually it will tell you, okay, I'm done. And then you have a directory called glimpse of lean. You go inside this directory, and it has a bunch of files. I mean, you can ignore most of them. The idea is that you will not work on them from the command line or from your normal file editor, if that's not VS Code. The idea is that you will execute the VS Code on this directory. You would write something like that. And let's see if you can see this as well. Obviously not, right? I should put it somewhere, like here. That's my mom. Hello, mom. Okay, so yeah, we're gonna have a problem there. Ideally, when you're working with these things, you want a wide screen or two screens. Is this readable? Yeah, even for Lazarus there, okay. Okay, so on the left you have this Explorer thing that shows you all the structure of your project. So you see it has some kind, okay, we're in this glimpse of lean, and inside it there are like 3 folders, exercise library solutions, and there is introduction.lean, and this has been loaded here. I'm not sure why, but maybe it just found it as a default thing, or maybe I clicked on it previously and I don't remember that I did that. And here you have the code, which is where you will be writing your programs / proofs. And here on the right hand side, it's like, this is extremely important, that if you are used to programming like traditionally, you are not used to having this kind of help here, which is what keeps track at any time of which are the goal and the givens that you have during your proof. So the idea is that even though there is a lean compiler and a type checker that will do things that traditional languages do, you don't keep writing code and then you compile it and then you run it and see how it works. The idea is that you develop the code interactively, having a dialogue with your system. In this case, the system is lean, and like the spokesperson for the system is like VS Code. So lean is running on the background. VS Code constantly has a connection with lean, and you'll see this in practice. Pretty much right now. Any questions so far? Okay, I will hide this. I'm not good with VS Code, I have to admit that, and I feel kind of a traitor even using it. But does anybody know how I can hide this? There's a shortcut. Wait, I know there's this thing, so if I write Explorer, no. Okay, what was it? Oh, of course, that's the one. Okay, and if you hover it, okay, I learned something now. If you hover it, you see the shortcut, so it's like Shift Command E, and I suppose if you, okay, I'll just forget that. It doesn't work to hide it. No, that's what I tried, but anyway, okay. Yeah, okay, so you click here, and then you have a shortcut to open it. I'm sure there's a shortcut to toggle it, but okay, it doesn't matter. So now maybe I can increase the size of the fonts, and they can be a bit more readable. Okay, I think it's readable, right? For everyone, okay. Luckily, the guy who made this thing, Patrick, has also given you right here in the comment. You can see it immediately. A tip. If you have a small screen, and we do right now, maybe you want to use Alt Z to toggle line wrap, so you don't have to go like scroll to the right and left. So okay, I will do this. These lights, yeah, you were late. There's no way to do that in this class. There are 4 switches there and 2 here. I have tried not all of the possible combinations, but some, and I haven't managed to turn this off. But if you do, I will be very grateful. Okay, so back on this. The first line says import something. We haven't had an import statement in our language. You will pretty much figure out and understand that the way we use lean, it's kind of similar to the way we were using our language of proofs. It's just that it's way more developed. I mean, but the primitives are the same. They're not similar. They are the same, and they are very few in number. And it's based on the type theory that we were investigating. And there are other proof assistants as well. This has become extremely popular among mathematicians, and this is why I'm using it. We could have picked Agda or something else, but let's do lean because of the audience we have in this class. So in the third line, you see something that says namespace introduction. Normally, you would ignore all these lines because you don't know what they do, and you will start reading the comments, and you know these are comments because they have a different color. Supposedly, you are used to understanding that gray things are comments. And you start them with this symbol there. So all those things lean will ignore. You will not ignore them because you are trying to learn lean, so you will read them thoroughly, which is something I will not do. I will kind of diagonally try to resolve this file, maybe the next as well, and then I will leave the rest of this tutorial to you. Okay. So yeah, namespace pretty much tells lean that the things we will be defining here will be like, how should I say, wrapped around something, let's call it introduction, so that I don't have classes with other names that may be available outside of this introduction thing. And that's pretty much what's to it right now. And if you read the comments, you will learn how you can write your own comments. For example, in this paragraph, you see that you can start you can do this thing to start a multi-line comment, or you can do something like a double hyphen, or I don't know, and you can have a single line comment. And as I said, these things are ignored by lean. So let's try to do something like a real life thing and go through it. So first of all, you see here a comment that says in natural language, in human language, in this case it's English, what it means for a sequence of real numbers to converge to L. So probably you already know that, and if you don't, or if you don't remember it, it's right there, and this is just for your human brain and your human eyes. And right after that, you see how you say this in lean. So def starts a definition, so I'm defining something, and I get to pick a name for that. And this may seem extremely, I don't know, inessential, the picking name, but if you've been following along this semester, you know how much emphasis I put in picking nice names. And in this case, they have named this thing sec limit, or sick limit, I don't know how you pronounce it. You could name it something terrible like foo, okay? Now you have named it like that. And after that come all the parameters that sec limit has, and in this case it has two parameters, and you can see the name that the person has chosen for the parameters as together with their types. So sec limit is something that has a parameter of a u, whose type is a function from natural numbers to real numbers. We tend to call these things sequences of real numbers, and a real number called L. And this whole thing, sec limit to when it has received its U and received its L, so the sec limit of U of L is the following. And now you start reading this pretty much the way you would read it, like it's for all epsilon greater than 0. Lean uses comma, and then language we have been using so far. Okay, sorry for this. Does anyone know how I can disable these things here?
Στο αυτό το command palette, μάλλον αν μου γράψει IntelliSense ή κάτι τέτοιο.
Right, what?
IntelliSense. Όπου, ναι, και ενώ ξέρω sense.
There's nothing that's... Okay.
Αυτά είναι μόνο για lean. Αυτό είναι...
Μία λέξη.
Δεν είναι...
Intelligence,
αυτό είναι Explorer των αρχείων.
Okay. Wait a bit. This is why the Explorer thing didn't work previously. Okay, I was wondering what I did wrong. Okay, so No. Okay. Okay. I'll try to ignore. What? You have a different idea?
No, to complete.
ή κάτι τέτοιο.
Not complete is good. I don't like the. Okay, anyway, I'll ignore them. Try to ignore them as well. Maybe you'll like them, I don't know. In our notation, we would be writing this like that, but that's, you will agree, a trivial change, right? And eventually you would do something in square brackets. Lim doesn't do it like that. You have the quantifiers and commas, and then the rest that you want to do. So let's try to read this for all epsilon positive. There is an n such that for all little n greater than or equal to n, the absolute value of this thing is less than or equal to epsilon. This should be understandable even if this was our first. This line should be understandable even if this was our first lecture. Okay, done. What have we proven? Nothing. We have just given indicative name for this weird thing here, this whole line. And notice that this whole line has some free variables, which are exactly the things that the parameters of sec limit. So if I just told you this thing, for all epsilon, blah, blah, eventually you would find it strange that there shows up a u there and an l there, okay? So we're parameterizing u and l, and we define sec limit. Sec limit of u and l means this. And again, we haven't proved anything, which have just given this a name. Okay, so sequences will be denoted here as functions from the natural numbers to the real numbers. This is pretty standard. We could rename this and have this something like a sequence of reals. We'll get to it maybe later today or in the next lecture. To be honest, I don't like thinking like that. Even in first semester things, trying to understand limits and seeing absolute values, for me it's very weird. I would prefer to see something like the distance of un and l is less than epsilon, or maybe even define what an epsilon ball means. I mean, do a bit of metric spaces terminology and notation, because it's way more intuitive than thinking of absolute values and stuff like that. But this is like a personal taste. Obviously, the person who created this tutorial picked up the more standard route to see this the way you usually see it in the first semester. Okay, so we are already used to writing f of x like that and not like this, so you can ignore this next comment. And now let's give a second definition of what it means for a function to be continuous at a given point. This function is as you can see here, continuous at needs two parameters. It's a function from reals to reals and a specific real number. We want to define what it means for this function to be continuous at this point. And if you remember it, it's exactly this thing. It's like for each epsilon, for all epsilon positive, there is a delta which is positive, such that for each x, and the idea is as long as x is delta near x0, then the image of x will be epsilon close to the image of x0. And you can consider this x0 like a center of a little ball or something like that. Yes, Konstantinos.
Αυτό είναι το ίδιο σύμβολο και για το arrow και για το implies.
Okay, so a very good question. This is very related to the whole theory we have been developing. So remember that the idea that propositions are types and types can represent propositions, but in a sense it's like a broader thing, types. So yes, I mean, when you think of these things, you look at it, and right now you would say this is an implication, because your mindset is like, I'm reading a mathematical proposition. But I mean, what is an implication in the foundation we're working on? It's like, it's a function that, given a proof of the left-hand side, it gives you back a proof of the right-hand side. So all these identifications will go on like that. Lin has picked this symbol for all, and can somebody remember what this corresponds to in type theory? Mm-hmm. Yes, these are the pi types. It's a product. It's a dependent function, right? And okay. Any other questions? Okay. Yes.
I see that like here and in the definition of I assume that can be done with inference, like.
Exactly. So it's a bit subtle, getting getting a good feeling of when you should write a type and when you shouldn't. If you're in doubt, write it. Okay. If it's too obvious, don't write it. The idea is that you are never forced to write it when it can be inferred, and there will never be some kind of ambiguity there. I mean, the Lean will infer the type, and if you provide the type and it's not in accordance to the type that Lean thinks from type inference, you will get an error, which is actually very good because sometimes you may think that you are proving something, like you're constructing something of a certain type, and Lean will accept it and you will be happy, but actually maybe what has happened is that you have proven something different. So if you had already declared the type of this thing, Lean would not accept it happily. Since you skip this part, Lean will say, okay, yeah, you proved what you thought you were going to prove, because by the context it seems like you wanted to prove this thing, while in reality in your mind you had something else. So it's a good, how can I say that? It's a good habit to be verbose, because sometimes you make some mistakes. In between, there's a gap. I mean, as soon as you teach this thing, you also understand this, that there's a gap between what the student writes and what they want you to write, right? And maybe what they write compiles, makes sense, but maybe it's not what you wanted to write. Yes?
Just to be sure that I have like the right feel for how inference works here. Here we would say, like for example, to understand what big N is, we see that U of small n is written there, so small n is a natural number, and since we're comparing small n and big N, that means that big N is a natural number.
Exactly. And it would be an overkill to write this down, because it's like immediately inferable, and this is why you will not do it. In this tutorial, I think, if I remember correctly, it's kind of a bit more of, it has some verbosities that normally you wouldn't do. Okay. But here, it's not. Here, it's the standard way you would write it. Other questions? Okay, there should be a question, unless you have been paying attention on Zulip since the beginning, but I mean, you see that there are some weird symbols here, right? And you are supposed to write a lot of these things. There are pretty much two ways you can do that. The first, which I highly recommend, is like, I will advertise my own product here, but I mean, find a way to do it globally on your computer. The other way is like VS Code helps you do it within VS Code, but there's no reason like to limit you to limit yourself in inside VS Code. Maybe you want to write here for whatever reason. I don't know if you can see the symbols here that I'm writing. Like, does Zoom work? Oh, it works. Okay. So I mean, it's very convenient to have a way to write. I mean, when you want to post something on Zulip. If you don't do that, you will end up opening a Lean project in VS Code and using these things to get access to the Unicode characters, and this is very painful, as you can understand. But let's see how you can do it in Lean if it's not your system or whatever. Okay, so it has this for all here. If I mouse over this thing, first of all, it tells you what it means. I didn't, like, this was a spoiler. Okay, I hope you didn't have time to read it, but okay, let's do this, that it will have no spoiler. So it tells you how to type it, in this case. You can type it by writing \exists or \x, and if you do this, exists, it became like that. I will not do it like that, but it's good to know that habit, and you can do it with anything you see. You hover on it. First of all, it tells you, like for example here, that its actual name is real, and it also has this fancy abbreviation because we are used to saying it like that. It has a description of what it is. It's a type R of real numbers constructed as equivalence classes of Cauchy sequences of rational numbers, because it kind of matters sometimes how you have constructed something, like in this case. It tells you what is the import statement that you need to import in order to get access to this type and all the tools that come with it. So it's import, mathlib, data, real, basic, blah, blah. And it tells you how you can actually type this character, because it's realizing that it's a fancy character. So it's \r, br, real, or bbr. It has bunch of ways you can type it. Okay. Okay. So now you know how you can type anything you see on a lean file inside VS Code. Okay. You may have guessed it. What the answer to my next question is, but okay. So sorry, I was here. So like in this this thing that I have right here, like for all epsilon greater than 0. This is syntactic sugar for something. Can somebody tell me what it was? I mean, it's not just a quantifier and a variable, because we have quantifiers, variables, and then a proposition in which probably the variable shows up. But in this case, it's like for all, and then it's a variable, and then greater than 0. So I mean, how does this get like translated, this sugarized? This was like, I think we saw this thing in the first or second class when we were talking about some sugar with formulas. Lazarus?
For each epsilon which has a type of real with the proposition that epsilon is greater than 0 almost.
This is exactly what it means, almost, but you translate it into like human language. My question would be, how would you translate this weird thing into the primitive language that we only have for all x, phi of x. I mean, we have something like that for all x in what we've been using so far. And here it's not like, it doesn't have this format. It's like for all x greater than 0.
But x implies phi of x.
Okay, say it, Sotiris.
But x implies phi of x.
X, no, if I say x implies, I mean I have a type error here. How can x imply anything? X is just an object in this sense. Well, you're almost there, you're just keeping something. So let me write it like that, and now write what the translation of this thing is. Knowledge?
For all x greater than 0 implies x.
Yes, I'm pretty sure Sotiris wanted to say this thing, but something happened there. Something like that, okay? So, and you could see that, that's why I said there was a spoiler. I didn't remember if you could see this thing, but so if I hover here, since it's not a normal for all, it's this syntactic sugar for all, you can see something like that. The notation, blah, blah, is shorthand for exactly what Sotiris and Manolis constructed here. And it says like similar for other binary operators, but let me just test you here. What would be this? Sorry, it's so the translation of this line is this line. What is the translation of this line? And what is the obvious mistake you can make here? Manolis, what's the obvious mistake you can make here?
The obvious mistake you can make is making an implication again.
Yeah, like copy paste and say, okay, I don't need to think. That's a bad idea in general. It should be this. But if I say that there exists an x greater than 0 such that something extra happens, I'm actually telling you that there exists an x such that two things happen. So it's a conjunction, right? And this is not what happens in the other case. In this case, I'm not telling you, okay, if I had asked you first for the existential, the obvious mistake would be instead of implication putting a conjunction there, which would be weird because I'm not telling you that all x's do two things. I'm telling you that about all x's, the following holds. These guys that satisfy this also satisfies the other thing, and about the other guys I'm not saying anything, right? Okay, this is pretty standard as a sugar and as a notation, and I mean, it's easy to make this mistake when you try to translate it, even though you would never reason in a wrong way if you would just see this in this way. Because in your heart you know how to reason about it, but when you are asked to make it formal, sometimes something happens. Yes, Konstantin?
Εδώ το είναι από το υπάρχει και μετά, άρα στη...
Yes, okay. In the syntax of Lean, pretty much the following, there might be some weird exception, but I think there isn't. I mean, whenever you see a comma, it's like in our notation would be open a square bracket and go as far as you can without piercing any parentheses. So, does that make sense? Yeah. Okay, so it's almost half an hour and we haven't proven anything, but we have defined a couple of things and we have seen some things. So also you might notice that in order to get access to the real numbers, we are importing these things. So mathlib is huge, and be warned that the standard practice here is that when you would create a project that you want to use mathlib, you will import all of mathlib inside this project. It will not live somewhere in your disk. So that means that if you want to play around and like follow 5 tutorials, you will end up with 5 copies of mathlib, and it's big. Follow the instructions when you install it so that you don't have to compile it yourself, because if you try to compile it yourself, it will take a very long time. But there are compiled versions that VS Code and from the command line also you can download them so that you don't wait for the compiler to do all these things. And so if I go to the first line, you see that I'm importing something which is not that thing, but obviously if I see what's imported there, eventually some of these modules that get imported will import this this thing that gives me access to the real numbers, which was mathlib something. Okay, so if I think you go there with F12, maybe. Aha, okay, yeah, that was right. So there's a new tab now. I was here, okay, and now here I see the imports of the thing I'm importing, and one of them indeed, the first line already, it imports mathlib data real basic. You get a good idea of what this should be. Probably basic stuff about the real numbers, okay? And then also it's importing something called ring theory, ideals, maps, and quotient depths. The names are pretty indicative. If you want to browse through something, you do the same thing, and you browse the library, and it's a good idea to do it as long as you don't get scared, because you get a grasp of the idiomatic phrases and the way people name things. It's very important to be consistent when you write a language like that. You don't want, in some case, for multiplication to refer to it something like mul, and some other times like mult. And if it's associative, you have to decide if you are going to name this thing like that, or whatever different thing, and stick to the conventions. Now, if you're writing code on your own, you can still break this. People do that a lot. Don't do it. Be consistent with your own mind. And if you try to write in something that the community writes, you don't have much liberty. I mean, follow the conventions that the community is following. Okay, so we have 5 minutes before the break. Maybe we should start trying to prove something. So, okay, here is our first proof. You probably have seen this exercise in some calculus or real analysis course. We want to prove that for the real numbers, f is continuous at a point if and only if it's sequential continuous, which means that any sequence that converges to this point in the domain, the images of the sequence converge to the image of this point. I mean, probably you have seen it. If you haven't, it's a nice exercise that we will prove right now. Notice that this symbol denotes composition, like we're used to. And if you want to know how you type it in Lean, you hover on it and okay. It will not work here because I'm inside comments, but it will work like here. Okay, so it's function.comp, its full name. And how do you type it? You type it \O, that's a very weird name, because it looks like an O, I suppose, or comp or circle because it looks like a circle. A lot of names have like semantic names, a lot of symbols have semantic names like comp, which comes from composition, and syntactic names like shape or formal names like circ, which comes from how they look like. It's a good idea to stick to semantic names, I think, but anyway. Okay, we have like 2 minutes before the break. I think it's, oh no, I want to say something before we start the proof. You see the word example here instead of theorem. Pretty much example means it's a nameless theorem. Normally you would say like, what's that? Cont implies seccont or something. You would come up with a name, not this one, because you should figure out a consistent naming thing, but let's say this is the name of my theorem. When you just want to test something without giving it a name, you just want to make sure that it's provable, this thing is actually valid, you can do this thing example. So the example still has parameters, but it doesn't have a name. So let's see what the parameters are. We need an f, which is from reals to reals, a function. We need the sequence u. We need a real number x0. And here comes if this was our first class, so far so good. This would be something that would seem weird at this point, and I'm hoping that it's not going to feel weird, thanks to the fact that this is like the 18th lecture or something. So the fourth parameter, okay, the first three are usual mathematical objects that every mathematician considers mathematical objects. The fourth thing is something that most mathematicians traditionally would never consider as a mathematical object. They would think that, okay, these are the things that are on my table, these three things are on my table, and the next thing is a hypothesis that the limit of u is x0. The sequence u converges to x0. And they would never consider this as a normal mathematical object on which you can apply operation, with which you can combine other mathematical objects and stuff like that. But we know that all these propositions, we have brought them, see them as types, and we consider the inhabitant of these types to be like evidences or witnesses or proofs of these things. So this would correspond to something like I don't know, something like this. Suppose sorry for the little stars, I don't know how this is very annoying. Okay, I mean, commonly you would see something like that, and then you would give it a label. But even if you give it a good label, like, I don't know, A or whatever, or this thing, you don't consider that it lives in the same table as your mathematical objects. It is not the case here. I hope you have appreciated that. So the fourth thing that I have is a proof that, or a construction that shows, or a proof that the sequence limit, so that the u converges to x0. So what is the type of HU? It's this thing, sec limit u, and what does this mean? I just defined it like above. Okay, we will see how I'll get it. And there's another parameter like that, another hypothesis. This is a very common convention to the names of the hypothesis to start with an H, and it's not completely arbitrary. It's a very good name here that has been chosen, HU, because it's like the hypothesis that's telling me the main thing about u. Okay, so the name of this thing, I named it HU. And then I have a hypothesis on F that is continuous at x0, and I will obviously name this HF. If I had like 3 or 4 different hypotheses on F, I would probably have to think of better names, like HF cont, it tells me that's continuous, or whatever. And finally, I reached the colon. Patience with me. So all these things this thing that I'm doing, I will now claim what is its type. So the type of all this thing is this: sec limit f of u, f of x of u. So pretty much what I'm trying to prove is this thing that's after the colon, and I'm claiming that this thing on the left will be an inhabitant, will construct an inhabitant of this type. Let's translate it, will be a proof of this proposition. Okay, so I need to prove this, and you see this double colon equals, which means at this point I am defining this nameless thing. Okay, maybe for the sake of like first thing, if I can, my theorem, terrible name. So at this point I'm telling, after the colon and the equal sign, I'm defining what my theorem does. And since it's a function which gets 4 things as inputs, it's like having written something like x, y, z, w equals, I don't know, x blah blah times z times w, something like that. If I had written something like that, I'm defining f with all those parameters, and I obviously have access to those parameters and it's their types and stuff like that. I'm doing exactly the same thing. There is a difference between def and theorem that we will talk about, but you can think of it as a def for the time being. And the only strange thing is that I'm saying I will not need to give a name to this thing I'm defining because I will never use it for the time being. So it's like, not for the time, sorry, ever. So it's like, example allows me to delete this thing, okay? And notice that right after this, there is this special keyword by, and you see the comments of what it does, but I'll try to explain it immediately here. It starts listening for commands, as we have called them, for me to prove this thing. But notice that the super interesting thing that we'll stop here for the break is that as soon as you moved your cursor, okay, pay attention where my cursor is, I move my cursor up and down, some things happen on the right, okay? So this is the interactive part. I'm having a dialogue with the system, and as long as I'm here, after the by, you see how it has updated itself. Okay, it works. So it tells me I have like one goal. It gives me all this, okay, I don't know how to point. It gives me all those things here that are what's available to me, the context, and their types. So what do I have? I have an f, which is from reals to reals. I have a u, which is a sequence. I have an x0, which is a real number. And I know that the u converges to x0. And the reason that I know this is because I have a proof of it, whose name is hu. And I also have another hypothesis, hf. And then you see the turnstile symbol, this proves, and then it's your goal. We are used to do this like in a single line, but you can appreciate that it would be very hard to read if it was a single line. Now you see it's given in a single line, and then after the turnstile, what you need to prove. Okay, so yeah, we'll stop here for a break, and we come back after like 10 minutes or something. Okay, so now I'm recording my screen. I think that I lost all the screen of the first hour. Let's hope that we'll have something. Okay, so where were we? The point was we were trying to prove our first theorem with the help of this tutorial. And so we were right here in the first line of the proof, which we haven't written anything yet. We have written this keyword by. So pretty much by tells you I am entering what is called the tactic mode, which means I will be listening for commands. And this is something to discuss a bit because we have seen that proving a proposition means constructing an inhabitant of the corresponding type. And the inhabitant of the corresponding type has superficially at least nothing to do with these weird commands that we have been developing, like suppose this, and choose the left thing, and separate by cases, or split the goal, and stuff like that. These are like imperative, this looks like imperative programming. We call them tactics, these commands in the proof assistance world. And while to construct a term, let's say I want to prove that A implies A, where A is some kind of proposition, if I write it in tactics, I will do something like, or let's make it more interesting. A implies A and A. How would I prove this? I mean, ignore the arrows, right? I'm just trying to use this as a blackboard right now. We would do something like suppose A, and then we would give it a name. So maybe if I'm trying to be more formal with this, something like this, maybe. And now I know that A is of a proof of A, and now my goal has been updated to show that A and A, right? And how do I do that? Yes?
Choose left.
I think you mean to say this the right thing, but it's a conjunction where you say choose. It's as if you had a choice. You split it, the left part and right part, right? So you would do something like split it in parts, and then you would say that the left part and here you need to prove A,
Exactly.
which would be exactly A because you had it, and then you had the same thing for R, okay? And now if you look at it, it looks exactly like a proof in the language of proofs we have been developing, and all those lines correspond, maybe some are comments, but in this case they are not. They correspond to commands, right? Okay, so what is the purpose of the commands and the purpose of the tactics? It's actually instructions for your reader to mentally construct the actual construction, the actual term of the type you are trying to inhabit. And whether it's better to use, tactics or to actually construct it manually, it depends on a lot of things. Some proof assistants make it easier it's more common to use them, have been designed with tactics in mind, like Lean or Coq. Some other proof assistants like Agda have been designed with constructing the terms by yourself, and they help you do that. And you are not limited. It doesn't mean that since we are using Lean, we will only use tactics. After all, you just saw that there is a command, a keyword like this by thing, that opens tactic mode, which means that if I don't use by, I'm in normal term constructing mode. How would we prove this without using all those silly tactics? In this case, I hope you will agree, if I want to prove this proposition, it's much easier to prove it without using instructions, without telling and instructing Lean or my system how to create a term. I can just create it, it's easier. Can somebody guess what would be an inhabitant of this type? Yes, Kostadinos? Or not? Half a hand? Yes, again?
HA tipo way.
Oh no, it looks like you are saying you will not use the commands, but what would that mean? It's like you think it's implicit to say suppose, but the idea is to construct something of this type. And now the question you need to ask is, how do I construct elements of this kind of type? What kind of type is this? The question is for everyone. What kind of type am I trying to inhabit? There are like few kinds of types. You get what I mean? I also called them races at some point, doing some RPG metaphors. Yes, Arati? It's the arrow type, right? So I need to see how do I create, what are the introduction rules for the arrow type, and I will find out that I construct functions using lambdas. Okay, so it would be something like lambda x, and now instead of the dot that we use, Lean uses this arrow. Sorry for that. It's like, it's the function that taken x, it gives you, and now I need to construct what? I need to construct an inhabitant of the n type, which is just, yes? What do you mean n? No. What is a proof of a conjunction? The ampersand is what forms the actual conjunction. What is evidence that A and A? What kind of thing is it, Manolis? It's a pair. So here I will have to use something like x. It's what you meant to say, but it's not what you said. You get, okay. So it's the function that gets an x and maps it to the pair of x and x. Be careful when you're writing. Okay, maybe they want to use like that. Okay. No, ignore this error here. I'll go back to my lambda. And actually, this one has a name. We know this function. What was the name of this function? Somebody remembers? It goes from any alpha and clones it and creates a pair of the same alpha that it received twice. Yes? No, it was not double, it was delta, but the name comes from diagonal. Because if you think what it does, it like takes all the x and creates the diagonal of the graph. Okay, but that's not important. I could have picked some other proposition that we didn't have a name for that already. But in this case, if you want to prove that, it's much easier to just say delta, and it will be this, right? Delta, sorry, the actual I meant to say. The actual format would be something closer to that. Okay. Be careful with these parentheses, they are not parentheses. They are what in LaTeX you may know as l'angle, and you type them, you hover here, and it has some ways to type it, okay? For creating tuples. Okay, so whether you do something using tactics, and the tactics instruct Lean how to construct the term, or whether you write the term itself, it's a matter of choice, and you can mix the two even in the same proof, and this is actually idiomatic. When you reach a point that creating the term is completely immediate and easy, you want to do that, you don't want to give further constructions. I mean, we'll see it right now in this example. Yes, Konstantinos?
Γίνεται να κάνουμε το αντίστοιχο για το disjunction.
Yes. Look, if it's provable, I mean constructively, you would be able to do that as well. In this case, you would do something like pick X, and now, wait, you want to do the same in term mode or in tactic mode?
Όχι constructively, πώς θα ήταν πώς θα το...
Okay, saying constructively does not answer my question, because whether you use tactic mode or term mode, it doesn't affect your constructiveness, right? Term mode. Okay. First, let's do it tactic mode, just to irritate you. Suppose HAA, and what would I do next? I mean, now I would choose. Yeah, okay. So I would go do. I think what we have ended up choosing as a name was left and right. Okay, so you go left, which means that now you need to prove A, and now you will do something like exact A. And there's a different proof, right? On the other case, there was no different proof. I mean, you can think a bit about it. It's not. These things are nice to think about. Here, there is a different proof which does this. Okay. Okay. So how would we do that here? I would need to inject X on the other term, and you would do it something like in left X if you pick the first alternative, or in right X if you pick the second alternative. Pretty much, you check your type, which is an arrow, and you see here that it's called OR with a big O, and you see the constructors of it, which are called in left and in right, and you also have some cheat sheet of Lean open when you start doing these things, and eventually you memorize them, and it becomes natural. Any other questions? Yes. No way. Wait. First of all, they are not unions and intersections. Like they are disjunction and conjunctions. The only thing that I will agree on is that I can prove this. That doesn't make them the same. I mean, if you see a proof of one thing, it has a very different form than a proof of the other thing. It's true that if you give me a proof of the left thing, I can prove the right one, and vice versa. So they are equivalent as propositions, provably equivalent, interprovable if you like, but they are very different. If I give you something of one or the other, you will use it in a different way, because they are different kinds of things, different types. You can argue and say, but the information I have is if you give me a proof of a conjunction or a proof of this conjunction, right? A and A, or of the disjunction A or A, I may have some different bureaucratic things to do, but eventually what I have in my hands will end up being a proof of A. And you're right. But technically, you cannot say that they are the same. And obviously, it will not be the same if I change this from A to B. Right? Okay. And it will no longer be interprovable. Okay, equivalent. So, let's start writing some commands. Okay. So the first command that this has already been written. I mean, it's a tutorial. Some parts are solved for us, and some other parts are not solved for us. And this one is solved for us. But the idea is that you don't read it. You put your cursor and you see how things change there. Okay, so we learned the first command, which I don't remember if we had written this as a command. I think so, or a similar thing, like you unfold the definition. Because you're looking at this thing, which has sec limit there, f of u, blah, blah, and maybe you don't remember what's this thing. So notice what happens there when, this is quite helpful a lot of times. You want to see exactly what happened. So I have my cursor on the first character of the command, and it has highlighted, I don't know if you can see it, but this is like red there. And as soon as I will proceed, in green, it will tell me what it got replaced with. It was much more readable in this sense, but maybe I don't know how to attack it. I mean, I don't remember what kind of beast is this. It's like an existential, a for all, whatever. So I do like an unfold, and now I know that it's a for all, and now I remember how I attack for alls. It's like, suppose, give me. And the equivalent of the suppose in lean is like intro. Forget these intros that has there. I will do my own commands here. I will do intro. How will I call it? I will call it epsilon. And now, if you remember that this thing was, this is terrible. Okay, if you remember that this thing was an syntactic sugar for all, and after that was an implication, it means that I'm just attacking the initial for all. So when I say intro epsilon, I just say, okay, give me an argument of this thing, which is a real number epsilon, and now let's see what's my new goal is. And my new goal, what happened here? Two things happened. First of all, I got an epsilon. You see this epsilon showing up there. And secondly, my goal changed. But my goal, look on what it changed. Now it's an implication. If epsilon is greater than 0, then blah, blah, blah. So how do I attack an implication? With intro again. So I need to think of a name, because now what? Okay, so important this thing as well. I didn't give it a name, and it became like an invisible hypothesis, which I cannot refer to. Sometimes this is enough because Lean can figure out how to use them by themselves. There's a lot of automation. It's a quite big mistake to start using the very useful, sorry for that, features of Proof Assistant when you're trying to learn how it works, because pretty much all of those theorems that we'll do eventually might be even self-provable, let's say automatically provable by Lean, but you will not end up understanding anything that goes on, although we will use today a pretty strong tactic. But like, okay, probably I will want to give it a name, and I will call it H epsilon. So now, after this second intro, I gain one more goal, and I gain one more given, which I called it H of epsilon. It's the information that epsilon is a positive number, and now my goal got updated again, and now I have an error because it's trying to do intros. So remember, you cannot use any command anytime you like. This is the whole point. And you have already guessed that instead of doing intro that and intro that and intro that, there is a macro tactic that allows you to do a bunch of, to introduce a bunch of things. So in this case, this is what we're doing here. We say, okay, and this is exactly how you would write it. You will not suppose this, suppose that, let that. You say, suppose this and this and this and that. Okay, so this is what intros correspond to. Suppose epsilon is a real number, such that, or in other words, and also suppose that it's a positive. And now you cannot, if you try to do something more, you get an error. Now you will not cheat like that. I mean, if you write it on a paper, someone will say, suppose n, that does exactly what half of the first semester students would want to prove an existential by supposing that exists. No, okay. Yes, so there are some raised hands while I was saying this. Yes, okay.
So all of these commands attack the goal, right? What if I wanted to unfold, for example, the definition?
Okay, so like, for example, you notice here, actually the unfold didn't even do a real step, right? But you're right, like there's another sec limit there that got intact. By default, unfold tries to unfold what's on the goal. If I'm not mistaken, I could do something like at and then say HU. Yeah, okay. And I could be, I mean, if you want to refer, at some point the default might be to do it on your goals, on your givens. So if you want to refer to the goal, you refer to it by the symbol. So this means, in this case, it's the same, because the default of unfolding something is unfolded on the goal, while if you want to do it on something different, you have to specify it. I'm not sure if this, yeah, this works as well. Unfold it anywhere. It's not a good idea in general. In general, you would prefer to see nice names, which is why we pick them. But right here, I mean, you just want to show unfold, and you were not even. It's not even a necessary step, because it's just syntactic sugar. I mean, you could skip it, but let's leave it there because it supposedly helped us figure this out. Okay, so at this point, what has happened? We have all the same things. We have an epsilon and a positive epsilon, and I want to show that such thing exists. Can somebody remind me how we prove that something exists? Don't look ahead. Yes. Yes, you use something, and actually, in this case, it's the same. It's the same. Command in Lean as our own language. You don't get to prove existential by telling me, oh, it's impossible that it doesn't exist. Okay, you have to give me your actual witness. And okay, let's see. What is the witness we will use here? I need to find an n such that from that thing, and where will I find this n? I could use something like 42. Lynn is happy with that. I will be sad soon because there is no way that I can prove what I'm doing now. So the fact that you made progress is not really a good idea because maybe it's regress. So how do you go on from there? You say, aha, okay, bad idea to use 42. Go back, okay? So that's a regress. So what will I use? And at this point, it's not very clear what I should use. I mean, if you have seen this 1,000 times, the proof, maybe you say, okay, use this thing. And especially in this kind of proofs with epsilons and deltas and n's, people lie to you. When you read a textbook in mathematics, you say these guys are geniuses. How did they come up with this weird, let epsilon be this, let delta be this weird thing? Of course, it's not like difficult, but for some reason, it's a common habit to hide how you got it. And we'll do something similar here, and we'll try to have a dialogue and figure out things, and then maybe we'll say, okay, let's hide it, and let's pretend we figured it all by ourselves. Okay, so we need some inspiration. Somebody has an idea on what I could do here in order to obtain this day. It's impossible for me to think in sequences without mentioning days and time metaphors. So I need to find a certain day from which onwards something happens, right? Okay, Manolis?
So we get for our specific epsilon a delta from our definition from our continuous function.
Okay, calm, okay. Yeah, you're right. So we have givens that we have not used yet, so let's try to use them. So what does it mean that f is continuous at x0? Let's rewrite that. Unfold continuous, or maybe mouse over it. I think that would be faster. No, okay. Sorry for that. So let's unfold it. Unfold continuous at fx0. It's like that. At hf. Okay. So now it's all those things. So we want to use this. What is its type? I want only the 5 races of types, or 7, or how many they are. I mean, it's a for all, okay, but I mean, how do we see what does this correspond to? Yes? Yes, it's a p, it's a function, okay, which means that in order for it to be useful, you need to give it an input of the appropriate type. What is the type that hf expects? An epsilon, right? It looks like it wants an epsilon greater than 0, but this is just syntactic sugar. It actually just needs an epsilon. So let's try to see what this. Okay, I will do a little trick here. Okay, foo is equal to hf of epsilon. Okay, and now if I do that in my givens, I also have this foo. I say obtain something that I will call foo by applying hf to epsilon, right? Okay, so what is this foo? It's a function that wants something, it wants evidence, a proof of epsilon greater than 0 in order to produce something. Do I happen to have evidence that epsilon is greater than 0? Yes? Yeah, so I could do something like now obtain bar of foo applied to h epsilon, and now I have also a bar, but I hope you appreciate now the purification and that I don't want to do all this thing one at a time. I can do hf applied to epsilon, applied to h epsilon, and now my foo is just the thing. There's no need to do this step by step, right? Okay, so now I have this thing, and now what is this thing? Yes? Which means, it's what? What are the inhabitants of, what does it correspond to? Konstantinos? It's a tuple, right? It's a pair. There's something like convention that you'll find out right now, like what is a 5 tuple? Like the 5 tuple is a 2 tuple of a thing, and a 4 tuple, which is a 2 tuple, and so on and so forth. But there is a sugar for this. I mean, we just write ABC, and the idea is this is a 3 tuple. Okay. Okay. So which means that this full thing is actually, how many things are in this tuple? It's kind of easy to get. Like, okay, let's see. You cannot see it here. It's here. There's you can cheat there. If somebody read it, ignore it. So it's an exists delta such that. What was the next? Okay, let's try to do it like that. Obtain bar. Our proof will not have all this nonsense. Okay, this is like what you could do on your scratch paper in order to figure out this delta before pretending that you were also smart and you figured it out by yourself. Okay, so let's. And the good thing is that your scratch paper talks back to you and has and doesn't let you make mistakes. So obtain bar, and now from foo, and I want to do it like this thing. Let's call them I don't know, UV. Terrible names. No, I already have a U. PQ. First of all, I'm not even thinking what kind of things these things are. That's why I named it in this terrible way. And now I can see what the types of these things are and maybe figure better names. So P is a real number because if you go back to foo, where is foo? Oh, sorry, I have distracted foo. Okay. Let's go here. Okay. So foo is an existential thing, which means that it's a pair of a delta and the rest. Okay. So in this case, my delta will be, let's call it delta, why not? And the rest. This is what I will know about delta. So this is a better name. Okay. There is a delta such that. Okay, but what is this such that? This such that is a pair. That delta is greater than 0 and also something. Which means that if I take a longer take on it, the whole existential thing, it was like 3 things. Because H delta itself was a pair, was a conjunction. So I could do something like that, PQ, okay? But I don't really need this. I could say, give me a delta, and what's the next thing that I know? I like the names that you can see below. So it's like, I need something that tells me that delta is positive, let's call it like that, and some hypothesis that I have extra, the rest of the stuff, right? So if I do it like that, at this point, I have a bunch of new stuff. I have a real number delta. I know that it's positive, and these are green because these 2 things are exactly what replaced foo that I used to have there. And now I realize that I don't even need this foo. It was completely inessential. I could do this like that. Are we following on what is going on here? If you see what the tutorial has written there, it's similar, but it's one of those times that the tutor here is being overly verbal. Normally you would not do that, but it says, I will, this will correspond to what we had like in claim something. You say, I will prove this, give me some time. And then you open a subproof, and then you do it, and then you go back, and you gain it on your givens. So this is very much what you normally do. You say, I will obtain something of this type, and here you see this type from this column all the way up to this, up to here. Say, I will manage to get something like that. And how will you do it? Then you say how you do it. In this case, you apply HF to epsilon to H epsilon. Which is exactly what we did, but we didn't give a name to this thing. So if it's very simple, you will not do it. If you want to keep track of what you are proving, you do it. I mean, and if you try to prove something different, if you make a mistake here, if you think that you are proving that for all x blah blah blah, you will get an error saying, wait, you said you could prove this, but this thing that you're obtaining has a different type. So either change what you're claiming you're proving or change your proof, right? Okay, so are we okay so far? Questions? No, okay. I'm going maybe overly verbose with all these comments, but the idea is like to discuss various things that may happen. Okay. Don't look, okay? So maybe you've seen it already. Why is this thing green? Because it just showed up in the thing I just did here. Right after the obtain, this got highlighted green. But I need to look at my goal. Still, I haven't made progress with the goal. I need to come up with a natural number that does something. But I have new givens. I have the delta, which is a real number, not very helpful. I know that it's positive, and I have a new hypothesis on delta, which for some reason I'm not allowed to use. Do I have two obtains here? Yes, I have two obtains, that's why. Okay, so perfect. So I have, I know that for all x, this thing that the continuity gave me, and I also have HU, which I haven't used yet, okay? So now I can get the n that I'm looking for together with this thing by just applying. Okay, let's see what I need to do. It's easy to forget that you're trying to prove something and just see this as a video game, and it will get you until some point. But I suggest you don't enter video game mode, because eventually you'll have to think and understand what's going on. Okay, and we hit this spot now, I think. Previously we hit this point and we asked Manolis and said, okay, let's use continuity. Okay, so what can we use now? How could h of f be useful? It's a function, which means I need to give it a real number, and I have a bunch of real numbers lying around, and I can create an infinite number of real numbers. So in order for this to be useful, I need to pick the right input so that I will know something about it. And what about sec limit? Let's unfold it as well. Unfold sec limit at HU. Okay, this is also a function, which means I need to pick the right epsilon in order to get a natural number. But now I am kind of getting happy here, even if I forgot what I'm trying to prove. I say, wait a minute, I need to find the natural number, and I have something that gives me a natural number. Maybe I can use that. Okay. So, any ideas? Okay, so that yes.
Use HU.
Yeah. So you use HU. You know that HU is okay. I hope you realize that this epsilon here and this epsilon here are completely unrelated, right? Maybe you would have picked something else, but this is a bound variable, and this epsilon refers to this epsilon, while this one is something available in my state. So I get to pick whichever real number I want, and here the useful thing would be to put the real number in as an argument. But actually, if I see this as a carried function, in order to use HU, even if I give it a real number, there is another input that it will immediately ask, which is the fact that this real number is positive, right? So I need to plug in as inputs to HU. Here's a real number. Here is a fact, a proof that it is positive. Now give me back the output. I could just apply the real number, but the output I would get back from the function would be a new function that it would still be waiting for a reason why epsilon or delta in this case is positive in order to give me something. Okay, so I will do it, it's already done here in one take. Again, normally you wouldn't use this, so let's delete it. And you would do something like apply HU to delta and delta positive, and what you get, which is this thing, there exists an n such blah, 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 let's call it n and HU. Why is it a pair? Because an existential, so it's a pair. The first part is the witness, and the second part is the rest. So we call the witness n, and the rest is HU. And if we are lucky, this n will be a good witness for what I'm trying to prove. And this is the next line. So let's see the intermediate step here. At this point, I have obtained a natural number. Again, this n here, maybe I should use a different name. Let's call it k, just to make it obvious. Okay, which means I should have called it here k. And since okay, let's leave it like that. So I'm saying I will use k as a witness, and notice what happens here. Your goal was to show that there exists an n such that there exists a big N such that big N is nice, and now it becomes there exists. Now it becomes you give big K there, so you still owe to show that big K is nice. And what does it mean to be nice? It means that starting from day K onwards, this thing happens. So now you know what to do. I mean, it's for all. So you need to prove that for all n greater than blah blah something happens. So you say, okay, give me an arbitrary n, I will call it n, and I could stop here. And in this case, what I did was I only asked for one input, but there were more inputs there, so we know what to do. Intros n and something that I will name hn because I have a hypothesis about the n I'm getting. And at this point, things are getting pretty nice. I have a bunch of things, which is good, weapons, and I need to prove only this thing. And now I look on my givens and I realize, hey, there is something that gives me that things are less than or epsilon, which is the HF, right? So probably I will need to apply HF. And up to now, I have only been using for alls by manually giving them inputs because I could see how I could use them in order to get the outputs. But there is a different way to use an implication. You pretty much say, I will get the thing I need to get by applying this function. So now Lin will tell you, okay, if you are to apply this function, then I will reduce your goal to producing me inputs for this function. Right? Does that make sense? If I want to prove that if I want to prove B, and I have that something implies B, and I say I will use this, I don't get away for free. I still have to say why the left-hand side is valid, right? Okay, so in this case, I could do something like apply HF. And it's okay. Let's see, was it an HF like that, or was it the HF it's like that. Good. So notice what happened in the goal. Sorry. I was here. My goal was to show that for any blah blah something happens. And then I'm saying I will get this by applying HF. What is HF? For all x, this thing is there. So if I do that, what is left for me to prove is the left-hand side of this implication. And notice that something. Okay, here Lin is being too smart. I don't want to skip this. I want to do it manually. Apply is a bit too smart. I was hoping to get an error here, but yeah, apply is smart enough to understand what the argument of HF should be. But let's try to figure that manually. Let's look at HF. HF is this thing, right? For all real numbers, if this happens, then that. And what my goal is before I apply this is the f of u applied to n minus this thing and all this absolute is less than or equal to epsilon. So I don't have a choice. If I want this thing to match this thing, okay, epsilon is epsilon, obviously, less than is less than, I have no choice here. This part after the subtraction sign is also no-brainer, there's nothing you can do. And the only thing that I would have to say something is like, what is the x here? But if I unfold this thing, let's unfold it. Unfold, maybe it's comp, maybe it's like that. Okay, so if I unfold this definition, okay, you see that it's now f applied to something, I had f of x, and this is where I'm saying that Lynn was a bit too smart if I'm trying to teach this. It's extremely convenient if I'm trying to prove this. I want Lynn to be able to infer things without me explicitly saying them. But right now, technically, what I would like to apply is HF applied on, what thing was it? UN. Okay, so let's try to see, let's do this little thing. HF applied to U of n. What is foo? Foo is an implication that gives me exactly what I want. So now I could do something like apply foo. And now I have exactly the thing I want in my givens. I applied foo, which means my goal has been reduced to the left-hand side of the implication, and I have exactly this in some part. So not only a matter of finding it. Where is it?
So HU.
It's HU, but I need to apply it to something. Because look, HU is not just this. HU is for all and blah blah. So I need to apply it.
HUHN.
You skipped an argument. HU means a natural number, and the fact that this natural number is greater than k in order to give the other. So I need to give two arguments to HU. Yeah, so I could, I don't know what I did. Okay. So now you can say something like exactly take HU, apply to, what was it? N and HN. Was it like that?
No.
And finally, after like 2 hours almost, we have reached this happy thing that says no goals. There are like an infinite different ways that you can write a proof. After you prove something, respect your future self and other readers of your code and delete nonsense like that. Obtain foo, blah blah. Try to figure out if there is a shorter or better proof. But as soon as you prove it, you can use this thing that you defined. Not in this case because we haven't given it a name because we called it example. Okay, but you could call it a theorem, and then you would be able to use it. Questions? Yes.
Για αυτό που είπαμε ότι θα κρύβαμε μετά το πώς υπολογίσαμε το K, νομίζω.
All of those things can be neatly hidden. I mean, since this is a tutorial, even this thing doesn't hide as much as it could, because the idea is to see this. But let's see, like, okay, just a second. Let me get out of this thing. Okay, this was the only proof here. Okay, nice. We have completed the first step of the tutorial, which was called introduction, blah, blah. Now that I have defined, I haven't defined it. Let's change the example, let's make it a theorem, so that I just want to make a point here. Okay, so like it's a theorem, let's call it cont in sec cont, I don't know. And so after this thing, I can ask for the type. I ask for types using this command, this check thing. So if I write something like this thing, I see on the right that 2 plus 3 is a natural number, and it's very important to notice that no calculation has been made. It did not sum 2 plus 3, see a result 5, and ask 5, what type are you? This is type inference. No evaluation has taken place. If I want to evaluate something, I use the eval, and if I do this thing, I see that it's 5. In this I can ask for, I can check what the type is of the, how did I name it? Contimsec, okay. And I see that, okay, you see this introduction dot something. This is because I'm inside this namespace and I don't want to confuse it with other files I may have. But let's see, it's on this thing. What is its type? Well, it's something that if it gets an f of this type, an n of that type, blah, blah, it produces an inhabitant of this type, okay? So essentially, it's a proof that for all those things, this sequence tends to this limit, okay? This is how I check. And if I want to see the term that link created following my commands, I can ask for it to print it, and I will see a huge, like, probably terrible looking thing. Why imps for some reason it didn't auto-complete this. So it's this thing. It's lambda, fun and lambda, this fun and lambda are synonymous for link. It's a lambda of all those things such that, and all those constructors that it does, and creates this term. Usually when you use tactics to create your terms are not that readable compared to if you had written them yourself. But the idea is you don't care, because link takes care of guaranteeing that everything is work, and the only thing that you care here is that you have actually a proof, constructed a proof of this. You have guided link to construct a proof term of that thing, pretty much. Questions? No questions. Okay, I have lost track of the time here. It's a good time to stop here. Obviously, the idea is to install all those things and start playing with those things and use Zulip to ask questions. There is something I need to mention here. Let me see if I can find it easily. Actually, no. There's something that I think that you will stumble upon some kind of mistake a lot. I will let you suffer enough in order for you to go to Zulip and say, why does this thing happen? Do that, and we'll discuss it there, and we'll also go on with this thing on the next lecture. So till Friday.